How are the galaxies in our universe organized? Are they structured and ordered, or are they randomly distributed? What laws govern the organization of galaxies? Many scientists, astronomers, and astrophysicists have tried to answer these questions. In 2023, we have even more technical means at our disposal to study the universe, and all its mysteries no longer seem as unattainable as before. We now know that the universe is made up of billions of stars, planets, comets, asteroids, and that all these celestial objects are indeed structured. First of all, stars are organized into galaxies. In the observable universe, there are an estimated 2,000 billion galaxies. Our own galaxy, the Milky Way, has between 200 and 400 billion stars and extends over an area of around 100,000 light-years. The galaxies themselves then organize themselves into galaxy clusters. These are galaxies bound together by the force of gravity. Galaxy clusters stretch from 1 to 3 tens of millions of light-years, and there are an estimated 25 billion of them in the entire universe. Clusters of galaxies are then organized into superclusters, structures ranging from a few tens to several hundred million light-years in size, with at least a dozen galaxy clusters. There are an estimated 10 million such clusters in the visible universe alone. Between the superclusters, there are zones of emptiness. In fact, 90% of the universe is made up of empty space. Impressive, isn't it? The universe is said to be lacunar. But let's take a closer look as we journey into the Virgo Supercluster. The Virgo Supercluster, also known as the local supercluster, is the supercluster of galaxies that includes the Virgo Cluster, home of the local group where our galaxy, the Milky Way, is located. This supercluster is gigantic. It extends over some 200 million light-years. Dear traveler, welcome. Today we're going to find out exactly what a supercluster is and see what the Virgo Supercluster, where our galaxy is located, looks like. We'll then take a tour of the most notable galaxies in the Virgo Supercluster. But before you set off on a new adventure, remember to like the video and subscribe to the channel so you don't miss a thing. Thank you, and fasten your seatbelt for immediate takeoff. But first, what exactly is a supercluster? We know that galaxies tend to cluster together, in groups of a few dozen galaxies, or in clusters of thousands. These groups and clusters of galaxies will themselves group together to form superclusters. Superclusters are gigantic groups of galaxies, sometimes hundreds of millions of light-years across. Each supercluster contains dozens of galaxy groups and clusters. In the Virgo Supercluster, for example, we find the local group, the group of galaxies that hosts our own Milky Way, as well as galaxy clusters such as the Virgo Cluster and the Furnace Cluster. The Virgo Supercluster is the best-known supercluster because it's the one we're in, but it's not the only one. The nearest supercluster is the Hydra Centaur Supercluster, which groups together two superclusters, the Centaur Supercluster and the Hydra Supercluster, separated by 150 to 200 million light-years. The Shapley Supercluster is another well-known supercluster located 650 million light-years away in the Centaur constellation. Superclusters are interesting for astronomers because it is on their scale that we can see the expansion of the universe. The expansion of the universe is the phenomenon whereby the objects that make up the universe on a large scale are moving away from each other. This is not, as we might think, the movement of galaxies away from each other, but a dilation of space. The expansion of the universe is the solution found by Russian physicist and mathematician Alexander Friedmann to explain why the universe has not yet collapsed under the effect of gravitation. When we observe large-scale celestial objects, such as superclusters of galaxies, this expansion translates into an increase in the wavelength of the light emitted by the galaxies. This is known as the redshift. In contrast, the blue shift is the decrease in the wavelength of light emitted by galaxies. The redshift reflects the apparent distance of celestial objects, while the blue shift reflects their approach. The expansion of the universe is not visible on the scale of galaxy groups or clusters. In galaxy groups and clusters, galaxies are gravitationally bound together, with a gravitational force strong enough to resist the expansion of the universe. But in the case of superclusters, the gravitational force is not strong enough, and the expansion of the universe makes itself felt. Clusters of galaxies are moving away from each other, albeit very slowly, but this is enough to increase the size of galaxy superclusters over time. For example, the local group is approaching the Virgo Cluster at a speed of several hundred kilometers per second or miles per second. Superclusters are of interest to scientists not only because they enable them to study the expansion of the universe, but also because they help them to understand the organization of matter in space. To study the structure of galaxy clusters, scientists have developed a method based on Hubble-Lemaitre's law. This method reveals the actual distribution of clusters in the universe, without the results being distorted by projection effects. Hubble-Lemaitre's law has made it possible to measure the distance to very distant objects. This law states that galaxies in the observable universe move away from each other at a speed roughly proportional to their distance. This means that the further away a galaxy is from us, the faster it seems to be moving away. To measure the distance of distant objects using Hubble-Lemaitre's law, scientists first perform a spectral analysis of the light emitted by the celestial body under observation. They then determine its redshift, before deducing its recession velocity, i.e. the speed at which the object is moving away from an observer due to the expansion of the universe. Scientists then use the recession velocity to calculate the distance to the object under study. While all this may sound simple, it can be very complicated with distant galaxies that reflect very little light. It can be difficult to obtain a spectrum of good enough quality to be usable. In any case, scientists have discovered that the distribution of matter on a large scale remains rather inhomogeneous. In other words, the superclusters are not evenly distributed, and there are huge gaps between some superclusters, which are spaces without galaxy clusters spanning several hundred million light-years. Astronomers have come to the conclusion that there are over 90% voids in the universe, and that galaxy superclusters are at the border between these voids, rather than the other way around. In fact, galaxy superclusters cluster together in filaments that form the contours of these vacuum bubbles. This reveals that the structure of the universe is far more complex than previously imagined. The origin of this structure is one of the questions that most fascinates today's astronomers, and they're hoping to get some answers thanks to the observation of superclusters. To explore the Virgo Supercluster, we have to leave our solar system, then our Milky Way galaxy, then the local group, the group of galaxies in which the Milky Way lies. The local group is one of the groups of galaxies that make up the Virgo Supercluster. We are now at the heart of this supercluster, some 200 million light-years across. The Virgo Supercluster is also known as the local supercluster. It's called the Virgo Supercluster because it contains the Virgo Cluster at its center. The Virgo Cluster is located around 65 million light-years from us. The discovery of the Virgo Supercluster was a gradual process. In 1863, William and John Herschel published the first major collection of nebulae, revealing that a large number lay in the region of the Virgo constellation. Nearly a century later, the Franco-American astronomer G.H. de Vaucouleurs then hypothesized that this excess of nebulae was in fact a galaxy-like structure, but on a larger scale. In 1953, he called this structure a local supercluster, and in 1958, a local supercluster. In the 1960s and 1970s, the scientific community was not yet unanimous on the nature of this structure, which could just as well be a random alignment of galaxies as an ordered structure. In the 1970s and 1980s, a redshift analysis showed that it was indeed a structure. The mass of the local supercluster was estimated at 10 to the 15th power solar masses. Much of this would be dark matter, since the supercluster's luminosity seems very low in relation to the number of stars in it. Contrary to long-held belief, the Virgo supercluster is not a gravitational structure with a clear boundary. In fact, the galaxies in this supercluster are not gravitationally attracted to the center of the structure, the Virgo cluster. Instead, they are attracted to a strange object outside this structure called the Great Attractor. We'll come back to this at the end of our journey. Incidentally, the Virgo supercluster is only a portion of a larger whole called Laniakea. Superclusters therefore appear to be structures of galaxies attracted to a large attractor, rather than structures of galaxies gravitationally bound together. Let's take a moment to study the structure of the Virgo supercluster before exploring its galaxies. In 1982, American astrophysicist Brent Tully illustrated the basic structure of the local supercluster. It would consist of a disk and a halo. The disk is roughly the flattened shape of a pancake and contains 2/3, or around 60%, of the supercluster's luminous galaxies. It includes 3 galaxy cluster subgroups: the Virgo Cluster, the Hound Cloud, and the Virgo II Cloud. The halo comprises 1/3 of the remaining elements, including many elongated objects. It's a more or less spherical halogen atom. The eastern local supercluster has no high-density nucleus. Where is the local group, and therefore our galaxy, located in this immense structure? The local group is located near the edge of the supercluster, in a small filament. It is attracted by the Virgo cluster, not the center of the supercluster. We're now going to look at the galaxies in the local supercluster. Astronomers have noticed that the elements of this supercluster are not arranged randomly. The density of galaxies decreases with the square of the distance from its center, located near the Virgo cluster. the majority of bright galaxies, i.e. those with an absolute magnitude greater than -13, are concentrated in just a few clouds. In fact, just 11 clouds concentrate 98% of the bright galaxies, including the Hound Cloud, the Virgo Cluster, Virgo Groups II and III, and Leo Group II. All in all, there are some 10,000 galaxies in the local supercluster, spread across some 100 clusters. Let's begin our journey into the heart of the Virgo supercluster by exploring the local group, where our galaxy is located. The local group is located on the outskirts of the Virgo supercluster. It comprises more than 50 galaxies. It is not possible to determine with certainty the number of galaxies in this group, as some are very faint and therefore difficult to detect, and the boundaries of the local group are not yet precisely defined. It is estimated to extend over a diameter of around 10 million light-years. In fact, it's considered a small structure, even if this may surprise you. So there could be far more than 50 galaxies in the local group, perhaps 60 or 80. What we do know is that the local group is organized around two spiral galaxies, the Andromeda Galaxy, or M31, and the Milky Way. Each of these two spiral galaxies is surrounded by satellite galaxies. For example, the galaxy closest to the Milky Way is the Great Dog Galaxy, located just 25,000 light-years from our own galaxy. A third spiral galaxy has been observed in the local group, the Triangle Galaxy, or M33. It is considered a satellite galaxy of the Andromeda Galaxy. In the local group, you can also observe two Magellanic spiral galaxies, i.e., single-armed spiral galaxies, the Large Magellanic Cloud and NGC 3109. These galaxies are smaller than ordinary or barred spiral galaxies. You can also observe an elliptical galaxy, M32, also a satellite of the Andromeda Galaxy. Elliptical galaxies contain only old stars, so according to astrophysicists, they are the result of the collision of two spiral galaxies. The local group also contains two dwarf elliptical galaxies, M110 and NGC 147. All the other galaxies in the local group are either spheroidal dwarf galaxies or irregular galaxies. Spheroidal dwarf galaxies are small, more or less spherical galaxies, often found in galaxy clusters. They are ancient galaxies that closely resemble globular clusters. Irregular galaxies, on the other hand, are neither spherical, elliptical, nor spiral-shaped. They are very luminous, rich in bright stars, but often too small to be easily detected. According to astronomers, they were once very numerous in the universe, but collisions have reduced their numbers. As a result, they now make up just 10% of the galaxies in the observable universe. Let's take a look at the Andromeda Galaxy, the largest galaxy in the local group. With a diameter of 220,000 light-years, it is larger than the Milky Way. It contains 2 to 5 times as many stars as the Milky Way, i.e., around 1,000 billion stars. As a result, It is 25% brighter than our own galaxy. But perhaps this won't last, as the Milky Way's star formation rate is 3 to 5 times higher than that of the largest galaxy in the local group. The Andromeda Galaxy is located in the Andromeda constellation, 2.55 million years from us. You can observe it with a naked eye from the northern hemisphere. It is thought to have been formed by the collision of two galaxies not so long ago. Astronomers estimate its formation date at less than 3 billion years ago, at a time when the Earth already existed. The Andromeda Galaxy and the Milky Way are approaching each other and will collide in around 4.5 billion years' time. The two galaxies will then merge to form a giant elliptical galaxy, along with their two central, supermassive black holes. The Andromeda Galaxy includes numerous satellite galaxies, notably the Triangulum Galaxy, the third largest galaxy in the local group. The two are separated by a distance of 750,000 light-years. This galaxy is unusual in that it has an HII region at its center, rather than a supermassive black hole, which is the most powerful X-ray source in the local group. The Milky Way, the second largest galaxy in the local group, is home to between 200 and 400 billion stars and over 100 billion planets. The solar system is located on the periphery of the galaxy's center, the supermassive black hole, Sagittarius A, precisely 27,000 light-years away. It's interesting to note that the Sun takes around 250 light-years to circle the center of the galaxy, so it's only been around 20 times since it came into existence. Our galaxy formed longer ago than the Andromeda Galaxy. Astronomers estimate its formation at 800 million years after the Big Bang. The oldest star in the Milky Way, HE 1523-0901, is thought to have formed shortly after the Big Bang, 13.2 billion years ago. Among the Milky Way's satellites is the Big Dog Dwarf Galaxy, the closest to us, located just 25,000 light-years away. This irregular dwarf galaxy contains just 1% of the Milky Way's stars and is being blown to smithereens by the tidal forces of the Milky Way. It is very likely that in the future it will disintegrate completely. The closest group of galaxies to the local group is the Sculptor group, or Sculptor filament. This group includes the irregular galaxy NGC 55 and the spiral galaxies NGC 247, NGC 253, NGC 300, and NGC 7793. All are very bright, although you won't be able to see them with the naked eye from Earth. Irregular galaxy NGC 55 lies at the boundary between the Sculptor filament and the local group, and is therefore the closest to us, at a distance of around 6 million light-years. It contains many stars in formation. NGC 253 is the dominant galaxy in the Sculptor filament, being the largest and brightest. You may have already seen the image taken by ESO's VISTA telescope at the Paranal Observatory in Chile. This image is impressive for its sharpness and precision. It's probably the most detailed wide-field image ever made of the Sculptor's filament. VISTA can see through the dust thanks to its infrared vision, resulting in a sharp, precise image. NGC 253 is also known as the Silver Dollar or Silver Coin Galaxy. It is an intermediate spiral galaxy located in the southern constellation of the Sculptor, around 11 million light-years from us. It was discovered by German-English astronomer Caroline Herschel in 1783, while searching for comets. From Earth, you can observe it with binoculars, as it's one of the brightest galaxies in the sky after our neighbor Andromeda. You can see it from the edge and make out its spiral arms and luminous core. NGC 253 is a good example of a starburst galaxy, i.e., a galaxy that is forming stars at a high rate. This process was probably triggered by numerous supernova explosions. In fact, you can see many bright clusters scattered around the galaxy. They're a kind of star nursery. You can see very young, hot stars that have just ignited, baby stars as it were. In the famous photo of NGC 253, we can clearly see that the radiation from these newly formed stars makes the surrounding clouds of ionized hydrogen glow. NGC 247 is also part of the Sculptor group. It is a faintly barred intermediate spiral galaxy in the Whale constellation. It was discovered by the German-British astronomer William Herschel in 1784, the brother of Caroline Herschel, who discovered the Sculptor galaxy. This galaxy is relatively unknown, as it is rather difficult to observe and photograph. A large instrument would be needed to obtain an image with enough contrast to clearly distinguish the galaxy. NGC 7793 is also a spiral galaxy in the Sculptor filament and the Sculptor constellation. It is one of the brightest galaxies in the group. Studies carried out by the Chandra Space Telescope have shown that this galaxy contains 22 X-ray sources, the majority of which are located in the Eastern Hemisphere. This may be explained by interaction with a nearby galaxy in the past. Before we set off to discover another group of galaxies close to our local group in the Virgo Supercluster, let's take a look at the Sculptor dwarf galaxy, which was the first spheroidal dwarf galaxy to be discovered orbiting the Milky Way. Long thought to be part of the Sculptor filament, it is now considered a satellite galaxy of the Milky Way. It is thought to be located around 280,000 light-years from Earth, but was only discovered relatively late, due to its low luminosity. The galaxy contains stars that are poor in heavy elements and therefore old. It is therefore an interesting galaxy for astronomers, as it may reveal valuable clues to the history of the earliest periods of star formation in spheroidal dwarf galaxies. We will now explore the IC 342 Maffei Group, another group of galaxies close to the local group. Like our galaxy group, it is organized around two substructures made up of massive galaxies, IC 342, and the pair formed by the two galaxies, Maffei 1 and Maffei 2. IC 342, also known as Caldwell 5, is an intermediate spiral galaxy located 11.4 million light-years from us in the Giraffe constellation. It is the most luminous and massive galaxy in the group. It was discovered in the 1890s. Like NGC 253, it is a star-forming galaxy. The IC 342 subgroup includes 9 known satellite galaxies, including NG 1560, the Giraffe A Galaxy, also known as Camelopardalis A or Cam-A, and the Giraffe B Galaxy, also known as Camelopardalis B or Cam-B. Maffei 1 and Maffei 2 are located in the constellation Cassiopeia. They were discovered rather late by Italian astronomer Paolo Maffei in 1968. Their discovery was not easy, as they were both hidden behind the plane of our galaxy and therefore partly obscured by interstellar matter. Maffei 1 is the closest of the large elliptical galaxies to us, while Maffei 2 is a spiral galaxy with a very pronounced bar. Like IC 342, the Maffei 1 and Maffei 2 pair has 9 known satellite galaxies, including Dwingaloo 1 and Dwingaloo 2, a barred spiral galaxy and its satellite, a small irregular galaxy. Both are located in the Cassiopeia constellation and were discovered late in 1994. Indeed, they are located at very low galactic latitude, in the avoidance zone, i.e. the area of the sky that is heavily obscured by the dust of the Milky Way. We're now in the Big Dipper. What you're looking at is the group formed by the galaxy pair M81-M82 and NGC-2403. M81 and M82 were discovered in 1774 by German astronomer Johann Elert Bode. Spiral galaxy M81 is the largest of the group, with a diameter of around 87,000 light-years. Although it can't be seen with the naked eye from Earth, it remains one of the brightest galaxies in the sky, which you can observe with binoculars. M82, also known as the Cigar Galaxy, is also a spiral galaxy. It is 5 times brighter than the Milky Way, and even 100 times brighter at its center. And with good reason. M82 is a veritable nursery of stars. A few million years ago, it is thought to have brushed against M81, triggering a huge wave of star formation in this galaxy. It's the closest star-forming galaxy to Earth, so it's much studied by astronomers. It was also in this galaxy that astronomers discovered the brightest pulsar known to date, the ultra-luminous X-ray source M82X2, in 2014. M82X2 is located 12 million light-years from Earth and emits an energy equivalent to 10 million times that of the Sun. M81 and M82 are in close gravitational interaction with NGC 3077, causing the formation of atomic hydrogen filaments between these galaxies. NGC 2403 is the second most important galaxy in the M81 group. It is an intermediate spiral galaxy discovered in 1788. Half the size of the Milky Way, it is home to numerous star-forming nebulae. You can clearly see its spiral arms, as well as small spots resembling star clusters. This was the first galaxy outside our local group in which a Cepheid was discovered. Cepheids are giant variable stars, or yellow supergiants, 4 to 15 times more massive than the Sun, and 100 to 30,000 times more luminous. 2 supernovas 16 times more luminous than average were also detected in this galaxy in late 2004. At that time, the galaxy's luminosity was more than 500 million times that of the Sun. The M101 group lies between the Big Dipper and Hound constellations. It is centered on the galaxy M101, the closest of the giant spiral galaxies, and contains at least 80 galaxies. M101 has a diameter of over 250,000 light-years, twice that of the Milky Way. It is one of the 10 largest galaxies in the Virgo Supercluster. It is also known as the Windmill Galaxy, or NGC 5457. Viewed from the front, when he discovered it, astronomer Pierre McCain described it as a starless nebula, very dark and very large. Yet M101 is said to contain 1,000 billion stars, 10 times more than the Milky Way. This group of galaxies also includes M51, or the Whirlpool Galaxy. M51 has recently moved closer to the galaxy NGC 5195, scattering billions of stars from NGC 5195 into intergalactic space and accentuating M51's spiral arms. NGC 5474 is also in the M101 group and may have collided with this galaxy in its recent history. It is a deformed spiral galaxy. Its nucleus is now very far from the center of its disk. NGC 5204 is a small, Magellanic spiral galaxy that emits a very powerful, ultraluminous X-ray source, discovered in 1980 by the Einstein Observatory, whose origin has yet to be identified. It could be an intermediate mass black hole. Finally, the group also includes the intermediate spiral galaxy NGC 5585, which has the particularity of having a much higher proportion of dark matter than other galaxies of the same type. We're now in the Centaur constellation. In front of you is the lenticular galaxy Centaurus A, or NGC 5128. It's the fifth brightest galaxy in our sky, and one of the closest radio galaxies to Earth. As a reminder, a radio galaxy is one in which most of the energy emitted comes from radio waves, rather than the usual components of a galaxy, such as stars, dust, or interstellar gas. Astronomers are therefore carefully studying its active galactic nucleus. In radio waves, Centaurus A extends over 20 times the apparent diameter of the Moon. Observations of this galaxy suggest that it swallowed a spiral galaxy around 500 million years ago, which would explain its intense radio emissions. Centaurus A's appearance is so strange that it wasn't until 1952 that it was classified as a galaxy. Seen from Earth, it resembles a lenticular or elliptical galaxy with a band of dust superimposed. Again, this strange morphology can be explained by the merging of two smaller galaxies in the past. While the bulge of the galaxy contains mainly old red stars, the disk contains over 100 star-forming regions. The Centaurus A Galaxy forms a galactic group with the two spiral galaxies, M83 and NGC 4945. M83 is located in the Hydra constellation and is often nicknamed the Southern Windmill Galaxy for its resemblance to M101. At its heart lies a star-forming outburst region, which is disrupted by a supermassive black hole that ingests huge quantities of matter while expelling matter and energy outwards. This is the galaxy that gave its name to the French electronic music group M83. As for NGC 4945, it's a barred spiral galaxy in the constellation Centauri that resembles the Milky Way. There are a few differences, however, which observations have revealed despite the galaxy being viewed from the edge. Its center is much brighter than that of the Milky Way, and it is believed to house a supermassive black hole that also ejects energy into space, while devouring huge quantities of matter. It has a highly active nucleus, meaning that its central bulge emits more energy than quieter galaxies. It is therefore classified as a Seyfert galaxy. We now turn to a spiral galaxy in the Peacock constellation, NGC 6744. It is accompanied by an irregular companion galaxy, NGC 6744A, which superficially resembles one of the Magellanic Clouds. Located 30 million light-years from us, NGC 6744 is considered to be a look-alike of our own Milky Way, although its diameter is twice that of our galaxy. It is one of the largest and closest spiral galaxies to Earth. Its apparent size in the sky is 2/3 the size of the full moon. Like the Milky Way, NGC 6744 has a dense, elongated central nucleus, a disk of dust, and spiral arms. Astronomers have identified at least 6 galaxies that belong to the same group as NGC 6744. Our discovery of the Virgo Supercluster continues with the galaxy NGC 7582. This spiral galaxy lies around 70 million light-years from Earth, in the constellation of the Crane. This galaxy was photographed by the MUSE instrument on ESO's Very Large Telescope to study the effect of an active black hole on star formation in a galaxy. Indeed, the central black hole of NGC 7582 feeds an active core thanks to the enormous quantities of energy it releases. The study of NGC 7582 shows that a structure surrounds the central supermassive black hole, diverting the flow of energy from the active core in the form of powerful winds to protect the rest of the galaxy. NGC 7582 is considered a variable active galaxy. In 1998, a sudden and unusual change in its optical emission line spectrum was observed for several months. Among the hypotheses put forward to explain this variation, astronomers considered the capture of a star by the supermassive black hole. Today, however, it is thought to be molecular material orbiting the active center, periodically occulting it, which gives rise to these variations. NGC 7582 is also thought to be a star-forming galaxy, with one strong burst occurring 6 million years ago and another 1 billion years ago. NGC 7582 is part of the Crane Quartet with 3 other galaxies, NGC 7599, NGC 7590, and NGC 7552. We're now in the constellation of Perseus. You're looking at the barred lenticular galaxy NGC 1023, discovered in 1786 by William Herschel. It's one of the brightest galaxies to be seen, just outside the Milky Way. With a diameter of around 60,000 light-years, it contains a supermassive black hole of around 44 million solar masses at its center. It's small enough to be difficult to see from Earth. You'd need a small telescope, a clear, pollution-free sky, and a time when the moon is faint or distant. The NGC 1023 group includes at least 19 galaxies in the Perseus, Andromeda, and Triangulum constellations. Most of these galaxies are either small spiral galaxies or dwarf galaxies. For example, spiral galaxy NGC 891 is the largest galaxy in the NGC 1023 group, with a diameter of 131,000 light-years. Seen from the edge, this galaxy in the Andromeda constellation is best known to astronomers for being the site of one of the brightest supernovas ever observed, SN 1986J. This supernova, discovered on August 21, 1986, had an apparent magnitude of 14. The Virgo Cluster is located at the center of the local supercluster. According to astronomers, it is the largest group of galaxies within a radius of 100 million light-years. The cluster is thought to contain between 1,300 and 2,000 galaxies, including 150 large galaxies and a large majority of dwarf galaxies. The diameter of the Virgo Cluster is 15 million light-years. Even the local group is smaller than the Virgo Cluster and is gravitationally attracted to it. The Virgo Cluster is organized around three main subclusters formed by the galaxies M87, M86, and M49. M87 is the largest galaxy in the cluster, with a diameter of 120,000 light-years. This giant elliptical galaxy contains over 10 billion stars, a supermassive black hole of 6.5 billion solar masses, and more than 10,000 globular clusters. M87 is surrounded by numerous satellite galaxies, including M98, M99, and M100, and the pair of galaxies known as the I Galaxy. As for the elliptical galaxy M86, it has the particularity of approaching the Milky Way at high speed. In fact, it's the second fastest approaching galaxy after M90, at a speed of 227 kilometers per second, or 140 miles per second, according to the NED database. It is also said to contain almost 3,800 globular clusters. Finally, the third major elliptical galaxy in the Virgo cluster is M49. It's smaller than M87, but still quite large, with a diameter of 124,000 light-years. Far from the cluster's center, it is nevertheless the brightest galaxy, and therefore the first to have been discovered in the Virgo cluster. It contains some 200 billion stars and 6,300 globular clusters. The M49 group contains more than 120 galaxies in the Virgo and Bernice constellations, including the elliptical galaxy M60, which astronomers believe could constitute a fourth subcluster in its own right. In the Big Dipper constellation on the flank of the Virgo cluster, we find a group of galaxies known as the Big Dipper Cluster or Big Dipper Group. Its luminosity is 30% that of the Virgo cluster, and its mass only 5%. This cluster forms a ribbon of galaxies in the northern hemisphere, most of which are spiral galaxies. The Big Dipper cluster is made up of two main groups. Ursa Major North comprises most of the cluster's large galaxies, located above 50 degrees north. This boundary remains rather arbitrary. The three brightest galaxies in the Ursa Major North group are NGC 3631, NGC 3953, NGC 4088, and M109. But these are not the only bright galaxies in the group. There are 32 galaxies with a diameter of over 30,000 light-years in this group. The second group in the Big Dipper cluster is Ursa Major Sud. Schematically, this group comprises galaxies located south of 50 degrees. The three brightest galaxies in the Ursa Major South group are NGC 3675, NGC 3726, and NGC 3938. The Virgo II groups are long filaments of galaxies stretching southwards from the edge of the Virgo cluster. In fact, they are a kind of extension of this gigantic cluster of galaxies. The Virgo II group begins at the level of the M61 and NGC 4753 groups, which form the southern edge of the Virgo Cluster. The filament then passes through NGC 4697 and NGC 4699. It ends 30 million light-years further on, with a group of galaxies centered on NGC 5084, a huge lenticular galaxy seen from the edge. M61 is one of the most remarkable galaxies in this long filament of galaxies. Located on the southern edge of the Virgo Cluster, this spiral galaxy seen from the front was discovered by Italian astronomer Barnaba Oriani in 1779 and observed on the same day by Messier, who initially mistook it for a comet. It is also one of the largest galaxies in the Virgo Cluster. It is also a star-forming galaxy. 8 supernovae have been discovered in this galaxy to date, the latest in May 2020. The M61 group comprises at least 32 galaxies. NGC 5084 is another remarkable galaxy in the Virgo II groups. With a diameter of between 250 and 300 million light-years, this lenticular galaxy is gigantic. In fact, it's one of the most massive galaxies in the Virgo Supercluster. Its mass is more than 10 times that of our own Milky Way galaxy. The Virgo III groups form a long chain of galaxy groups to the left of the Virgo cluster. It spans more than 40 million light-years. Why such a long distance? It seems that the gravitational pull of the Virgo cluster has contributed to the stretching of this chain of galaxy groups. Astronomers have estimated that the Virgo III cluster comprises 8 galaxy groups and 13 galaxies outside these groups. Among the galaxies in the Virgo III groups is the spiral galaxy NGC 5248, which is one of the brightest in its region, and the brightest in a small group of galaxies. It has a special feature that has been observed by the Hubble Space Telescope. Around its nucleus are not 1, but 2 star-forming disks. NGC 5364 is a spiral galaxy with very long spiral arms. This feature allows it to be classified as a grand-style spiral galaxy, a title deserved by only a tenth of spiral galaxies. This galaxy is beautiful to look at, even if its spiral arms are slightly asymmetrical and distorted, certainly due to interactions with a nearby neighboring galaxy. Let's continue our exploration of the Virgo Supercluster with the elliptical galaxy NGC 4697, located in the Virgo constellation some 40 million light-years from Earth. NGC 4697 is an active galaxy with a faint core. According to a 2008 study, it contains a supermassive black hole of around 170 million solar masses. It is also home to numerous X-ray sources and is surrounded by a halo of hot gas. These characteristics suggest that this galaxy has had a turbulent past, with supernovae, black holes, and neutron stars belonging to binary star systems, all of which could be the origin of X-ray sources. In fact, a large number of X-ray binaries have been discovered in the galaxy's globular clusters. What's more, since black holes and neutron stars are the final stages in the life of a massive star, astronomers believe that this galaxy was home to many massive stars in the past. The NGC 4697 group includes at least 19 galaxies, including the barred spiral galaxy NGC 4731, which measures over 80,000 light-years across. Its spiral arms contain a large number of young blue star clusters. You may notice that its spiral arms are distorted. This is due to interaction with a giant elliptical galaxy called NGC 4697. In the NGC 4697 group, you can also see a small spiral galaxy called NGC 4775, which also has deformed spiral arms, in addition to an off-center nucleus, and the barred spiral galaxies NGC 4941 and NGC 4948. In the Hound Dog constellation, you can see a vast spiral galaxy whose nucleus is surrounded by a star-forming disk. This is NGC 5033. This magnificent galaxy would have a perfect shape if it hadn't crossed paths with another galaxy during its history, slightly distorting its spiral arms. Its active Seyfert-type galactic nucleus is particularly bright, and is certainly home to a supermassive black hole that absorbs large quantities of matter. The brightness would then be due to the hot gas in the black hole's environment. Observations of this galaxy have shown that the location of the active core does not correspond with the galaxy's kinematic center, i.e. the point around which the galaxy's stars revolve. This would mean that the galaxy has certainly undergone a merger. This shift is certainly the primary cause of the core's brightness. Indeed, the shift between the nucleus and the kinematic center can destabilize the rotation of the gas at the galaxy's center, causing the gas to fall into the nucleus. The gas is then compressed by the enormous gravitational forces of the core center and becomes hot. NGC 5033 forms a pair with another galaxy called NGC 5005, but they are not close enough together for gravitational interaction to cause tidal forces and distort the galaxies. The gravitational interaction between these two galaxies remains fairly weak. In any case, we know that NGC 5033 is part of the NGC 5005 group, along with other galaxies. Astronomers disagree on the number of galaxies in this group, but there could be between 4 and 16 members. Let's continue our exciting journey into the heart of the Virgo Supercluster with an exploration of the Hunting Dog Cloud. Also known as the Dogs 1 Group, the Canes 1 Group, or the M94 Group. This cluster of galaxies spans the constellations of the Hounds and Bernice's Hare. It doesn't contain many noteworthy galaxies, so it's only very recently that we've been able to distinguish this group from the many other background galaxies in this region of the sky. In fact, it contains mostly medium-sized dwarf galaxies, ranging from 5 to 25,000 light-years in diameter. The largest galaxy in the Canes 1 group is the spiral galaxy NGC 4244, with a diameter of 65,000 light-years. This galaxy is seen from the side. Spiral galaxy NGC 4395 is a good example of a Seyfert galaxy, with a very bright core and faint spiral arms. However, it remains very faint and therefore difficult to observe. In the Dog 1 group, you'll also be able to observe NGC 4214, a small, irregular, hydrogen-rich star-forming galaxy of interest to astronomers because it contains stars in various stages of formation. Observations of this galaxy have shown complex patterns of glowing hydrogen formed during the starbirth process, but also clusters of much older red supergiant stars. Before continuing our journey, let's take a look at the spiral galaxy M94, which gave its name to the Dog Group I, also known as the M94 Group. It lies at the far end of the cluster and has a diameter of 30,000 light-years. It's a star-forming galaxy that's magnificent to observe. Yes, not only is it seen from the front, but it also boasts a beautiful ring of bright blue stars and well-defined spiral arms. In any case, astronomers haven't yet tired of observing it, and are currently trying to unravel the mysteries of its starry outbursts. The Hunting Dog's cloud should not be confused with the Dogs II or Cain's II group, which lies behind it. Also in the Hound's constellation, this galaxy cluster contains a remarkable galaxy, M106. Discovered by Pierre McCain in 1781, it wasn't added to Messier's catalog until 1947. And yet, this galaxy is particularly large and bright. It is 130,000 light-years across, larger than our own Milky Way. Its morphology is unusual. 2 spiral arms are clearly visible, detached from the rest of the galaxy, which is not very bright. The most precise images of this galaxy show that it may actually have 4 spiral arms. It is not known, however, whether these 2 additional arms are made up of stars or simply gas. In the same images, impressive jets of matter can be seen on either side of the nucleus, indicating that M106 is a Seyfert galaxy with an active nucleus and that it contains a particularly active supermassive black hole at its center. The galaxy NGC 4217, often presented as a companion galaxy to M106, appears smaller but is in fact of equivalent dimensions. It's simply not as close to us as M106. However, it's not certain that it's really a companion to M106, or even that it belongs to the Cain's II group, as some measurements estimate it to be 60 million light-years away from us, further from M106 than it is from the Milky Way. We're now in the Lion constellation. You're looking at the Leo 1 group, which is made up of 3 subgroups. On the right, the M96 subgroup, and on the left, the M66 group, and in the middle, the galaxy NGC 3489. The M96 group includes M96 and M95, 2 barred spiral galaxies, and NGC 3377, an elliptical galaxy. All 3 are particularly bright. M96 and M95 were both discovered on the same evening, March 20th, 1781, by Pierre McCain. They are slightly smaller than our own Milky Way. Both feature an inner star-forming disk close to the nucleus, whose secrets astronomers are trying to unravel, in particular, the links between these disks and the central black tower and spiral arms. Let's take a look at the M66 group. It's also known as the Lion Triplet. It includes galaxies M65, M66, and NGC 3628. Their magnitudes make them easy to observe, especially M65 and M66, which are often photographed together, making the Lion Triplet the most beautiful group of galaxies in the Lion constellation. M65 is a spiral galaxy, and M66 a barred spiral. As for NGC 3628, it's a magnificent spiral galaxy seen from the edge, with clearly visible dust bands. We can also see a trail of stars that have been torn from it by the gravitational forces between the three galaxies. In the past, interactions between NGC 3628 and M66 strongly affected the morphology of M66, which now has a more elongated spiral arm and a more diffuse halo. NGC 3489 is located in the Leo 1 group, between the two subgroups of M96 and M66. This lenticular galaxy interests astronomers for its hybrid characteristics. It has a prominent galactic bulge and a visible central disk, like spiral galaxies, but no spiral arms. It also borrows characteristics from elliptical galaxies, with little ongoing star formation and stars over 1 billion years old. Like many of the galaxies in the Virgo Supercluster, it is a Seyfert galaxy with an extremely bright core and a central black hole that devours any matter approaching it. The radiation from its active galactic nucleus, however, is weaker than average. See that vast gathering of galaxies to the right of the Virgo cluster? Those are the Leo II groups. These groups of galaxies lie behind the Leo 1 group and are spread over 30 million light-years. The elliptical galaxy, NGC 3607, is the brightest in the Leo 2 group. Among the other brightest galaxies in this area of the sky, you'll also find NGC 3169, a highly distorted spiral galaxy. It can be seen in the Sextant constellation, just below the star Regulus in the Leo constellation. Gravitational interaction with its neighboring galaxy, NGC 3166, has taken its toll on its magnificent spiral shape, and it now looks as if it's completely disintegrating. Astronomers wouldn't be surprised if the two galaxies were to merge. In Leo Groups II, you can also observe a curiously shaped spiral galaxy, NGC 3187. It features very open spiral arms. As for spiral galaxy NGC 3227, it's glued to dwarf elliptical galaxy NGC 3226. Both are among the 338 galaxies listed in Halton Arp's Atlas of Peculiar Galaxies under the name ARP 94. According to American astronomer Halton Arp, they are a good example of a spiral galaxy with an elliptical companion. However, there is nothing to suggest that they are in fact interacting gravitationally, especially as the distance between them remains relatively large, at around 9 million light-years. Let's continue our journey towards the Furnace Cluster. But before we do, let's take a look at a remarkable galaxy called NGC 2997. This grand-style spiral galaxy is located in the constellation of the Pneumatic Machine, a constellation you may not have heard of often since it's located in the southern hemisphere and is relatively faint. NGC 2997 was discovered by William Herschel in 1793 and lies around 55 million light-years from us, but is moving away from us at around 1,100 kilometers per second or 680 miles per second. This galaxy is particularly remarkable for its nucleus, surrounded by a string of giant clouds of ionized hot hydrogen. The NGC 2997 group comprises some 15 galaxies, including several irregular Magellanic galaxies. Before arriving at the Furnace Cluster, the Dorado group is also worth a visit. Call it a group, but it's more likely to be a cluster of galaxies given its size. The Eridan Group comprises spiral and elliptical galaxies. It is organized around two interacting galaxies, the elliptical galaxy NGC 1549 and the lenticular galaxy NGC 1553. These are the two brightest galaxies after the spiral galaxy NGC 1566, considered the dominant galaxy in this group. NGC 1566 and NGC 1553 are disk galaxies, which is the dominant galaxy type in the Eridan group. Astronomers therefore consider this group to be even richer than the local group. We're now looking at the Furnace Cluster, the only other cluster within 100 million light-years of us that's almost as rich as the Virgo Cluster, though still a little smaller. The Furnace Cluster is of particular interest to amateur astronomers for its compact core of galaxies, spread over just 2 degrees of sky. The two dominant galaxies in the Furnace Cluster are NGC 1316 and NGC 1365. They're bigger than any galaxy in the Virgo Cluster. NGC 1316 is a massive lenticular galaxy, which according to observations absorbed a spiral galaxy around 3 billion years ago. This was probably not the only galaxy to be cannibalized by NGC 1316. Not far from this galaxy is a spiral galaxy called NGC 1317, which could suffer the same fate. NGC 1316 is also a powerful radio source, known to radio astronomers as Fornax A. It is the most important source of radio waves in the constellation Furnace, and the fourth most intense radio source in the sky. These radio waves come from falling matter inside the supermassive black hole at the center of the galaxy, probably fueled by interactions with other galaxies. NGC 1365 is the best-known galaxy in the Furnace Cluster. It is a magnificent barred spiral galaxy of great style. Discovered in 1826 by Scottish astronomer James Dunlop, it lies in the southern constellation of Furnace and is studied by numerous telescopes. Its bluish color is due to a very high rate of star formation. This can be explained by the presence of a bar that connects the two spiral arms and compresses the gas present in the galaxy, triggering the birth of multiple stars. The Eridan Cluster is another remarkable galaxy cluster in the southern hemisphere. It is sometimes referred to as the Furnace II Cluster. This is because it is very close to the Furnace Cluster at a distance of around 20 million light-years. The Eridan Cluster is further away than the Furnace Cluster, at around 75 million light-years. These two clusters and their surrounding galaxies are sometimes referred to as the Furnace or Deep South Superclusters. The Eridan Cluster contains around 200 galaxies. Its galaxies are scattered over a larger area than in the Furnace Cluster, so it is less impressive than its neighbor. Two subgroups can be distinguished, one to the south around NGC 1395 and one to the north around NGC 1407. NGC 1407 is a vast elliptical galaxy, larger than the Milky Way, with a diameter of around 243,000 light-years. Its group contains at least 9 galaxies. NGC 1395 is also a vast elliptical galaxy, but slightly larger, with an estimated diameter of around 264,000 light-years. The NGC 1395 group contains at least 32 galaxies. We can't leave the Eridan Cluster without a quick look at NGC 1232, one of the most beautiful galaxies in the cluster, with its well-defined spiral arms. This stylish spiral galaxy is around 145,000 light-years across, and its spiral arms contain millions of bright stars, alongside dark dust, to the delight of our eyes. We've taken a tour of the Virgo Supercluster. This trip will have given you a glimpse of all the types of galaxies that exist in the observable universe, with near-perfect spiral galaxies and spiral galaxies distorted by the movements of the universe, giant galaxies and dwarf galaxies, active galaxies, and galaxies where no stars are forming anymore. But you should know that the Virgo Supercluster won't remain frozen like this for long. The universe may be moving slowly, but it's moving all the same. The Virgo Supercluster itself is constantly changing. It is attracted by the Great Attractor, a gravitational anomaly located near the ruler cluster. But what exactly is the Great Attractor? The discovery of the Great Attractor dates back to 1977. American astronomer Vera Rubin and her colleagues at the Washington Institute discovered that the Milky Way was moving faster than the expansion of the universe. The astronomers hypothesized that there was a force with a gravitational effect on the Milky Way, without knowing exactly what it was. A team of 7 researchers from the Cambridge Institute of Astronomy and the Washington Institute of Astronomy was formed to investigate the question. For the record, this team was nicknamed the Seven Samurai. To unravel the mystery of this unidentified gravitational force, the researchers measured the proper velocity of a large number of galaxies in order to determine in which direction the Milky Way and the local group were moving. 400 elliptical galaxies in the Centauri region were studied over a 5-year period. In 1986, the researchers from this small team discovered that the local group, as well as the Virgo Supercluster, were moving at a speed of around 625 kilometers per second, or 390 miles per second, towards a point they dubbed the Great Attractor. This point lies beyond the Hydra-Centaur Supercluster, in the direction of the Southern Cross, some 150 million light-years away. Scientists have calculated that the gravitational force of this mysterious attractor is equivalent to that of a supercluster, over 10,000 times the Milky Way. And yet, no visible mass has been identified. Here is a spine-chilling anecdote. Foucault's pendulum in the Pantheon in Paris points in the same direction, but no one knows why. An even more mysterious fact. In the region of the Great Attractor, the natural speed of galaxies is that of the expansion of the universe. And once past this fictitious point, galaxies have a speed slower than that of the universe's expansion, and some even show a blue shift. But the presence of the Great Attractor alone cannot explain these speed variations. In fact, other researchers have measured the radial velocities of galaxies in the Perseus and Pisces clusters, which are located further from the Great Attractor than the Milky Way. And it appears that they are drawn faster towards the Great Attractor than our galaxy or even the Centaurus or Hydra clusters located closer to this fictitious point. Researchers have put forward all kinds of hypotheses, including the presence of another Great Attractor or the imprecision of radial velocity measurements due to the uncertainty linked to galaxy luminosity. In 2016, after 30 years of research, researchers identified the existence of large extragalactic structures that could explain the gravitational attraction of galaxies towards the Great Attractor, without, however, completely solving the mystery. We've come to the end of our journey through the Virgo Supercluster, but we're not done exploring the universe yet. The Virgo Supercluster is part of a larger whole called Laniakea, and Laniakea itself is just one of the 6 million superclusters that exist in the observable universe. So there's still a long way to go before we understand all the mysteries of our universe and its organization. In the meantime, we can marvel at the beauty of galaxies and stars, and the way they are arranged in the sky, whether by chance or not.